Let's take a look at 2.4. Graphs that enlighten and graphs that deceive. There's all kinds of ways to organize data in graphs and charts to show people the data visually. Okay, some graphs are better than others. You saw earlier in the chapter, or the last chapter, that if you were to make a bar graph and label your y-axis or your x-axis in a certain way, then you can make the data appear to be maybe bigger than it actually is or smaller than it actually is. So that's one way that people are deceived really on a day-to-day basis with commercials and with ads in paper. A lot of times the charts and the information there is presented in such a way to make you want to believe one way when actually it's not that big of a difference, or it's wrong altogether. One of the ways that you can organize data is called a scatter plot. You really don't have to know these definitions. I'm not going to give you a definitions test, but you might want to write them down just so you'll know what a scatter plot is. You would more be along the lines of have to construct a scatter plot. And a scatter plot's really easy because all it is, it's like a XY plot of quantitative data with a horizontal x-axis and a vertical y-axis. So just like the rectangular coordinate system that we use, you have a horizontal x-axis and you have a vertical y-axis. Alright, that may look a little different, but if you just think about the x and y-axis of our rectangular coordinate system, that's what we use in a scatter plot. Alright, so your book says that the horizontal axis is used for the first variable, which is x, and the vertical axis is used for the second variable, which is y. Just like an ordered pair, x, y. You know, once you were to graph all of these points, then you can make a scatter plot. All right. Here's an example of a scatter plot. See, we have a horizontal axis, that's like the x. You have a vertical axis, that's like the y. Notice that it's really just the first quadrant. So if I went back to my graph, it's like, you don't worry about this here, don't worry about this here. We just have the first quadrant here. And that's where we put all of our points when we plot those. Okay. So this is a good example of a scatter plot. So it really just depends on the information that you have. You know, what are you pairing up? A weight and a pulse rate. That's what's done here. In figure 2.7, figure 2.6 was a waist circumference to an arm circumference. So the two topics, they don't have to be related. It's not that one depends on the other. Now you may be using a scatter plot to try to figure out a trend about the data or to show something. Then it would matter what you paired up, but it doesn't have to. It just really depends on the type of data sets that you have. Okay. So here's another example, scatter plot. You know, what could you tell about this set of data? Well, it says weight of pennies and years of production. So what could you tell? Well, you could tell that as the years pass by, you know, past probably 1985, 82, 83, the weight of pennies started to decrease because here's all the weights here. But before that time, the weight of pennies was up here at 3.1 grams. So, you know, you can get useful information like that from a scatter plot, but the first thing you have to do is construct the scatter plot. So, and it's nothing other than, you know, making a horizontal and a vertical axis, labeling them correctly, and then plotting the points. Another type of graph is a time series graph. A time series graph is a graph of time series data, which are quantitative data that have been collected at different points in time, such as monthly or yearly. The best example of a time series graph that I can think of is if you've ever looked at a stock and looked at how that stock is done over a period of time, or if you've looked at the Dow Jones Stock Exchange, or the Dow Jones average for the New York Stock Exchange over a period of time. You'll see lots of increasing and decreasing. You know, if there's a lot of decreasing, that means that it's going down, down, down. Of course, you can see here between 1980 and somewhere past 2005, probably about 2008 or so, they have the years and the Dow Jones graph, and so it's years versus the actual Dow Jones average, or whatever that is that's calculated, and that creates a time series graph. Alright, dot plots. I think about dot plots kind of like tally marks. If you were tallying up frequencies for different classes, it's kind of similar to what a dot plot is. A dot plot consists of a graph in which each data value is plotted as a point or dot along a horizontal scale of values. Dots representing equal values are stacked. So what does all that mean? Well, here's an example of a dot plot. So you can see they have, it's kind of like just a number line. You have your values down here. These don't have to be quantitative. These could be months, or these could be colors or something like that, just depending on the type of data that you have. But then you take each piece of data, each data item, and you put a dot at whatever it corresponds to, in this case IQ scores. And if you have multiple at that same number, you just stack the dot on top of the other. So you can see, like for an IQ of 50, if you recall that same data set we were looking at earlier in the chapter, there was only one IQ of 50 in that data set. Well, here it is graphed in a dot plot, or I guess I could say plotted in a dot plot. You know, there was one that was like 142 or something like that. Here it is right here. There must have been 3 that were 80 in that chart, because you see above 80 we have 3 dots. So dot plots are pretty easy to understand as long as you understand, you know, how they're presented. So now, to me, whenever I first saw this type of plot, this was the most confusing, because I had never seen it used before in any way. And it's called a stem plot. All right, a stem plot, or a stem and leaf plot, represents quantitative data by separating each value into 2 parts. The stem, such as the leftmost digit, and the leaf, such as the rightmost digit. Again, a stem plot, or stem and leaf plot, represents quantitative data by separating each value into 2 parts.
This was the easiest one to do, though. This is the easiest one. Because I really separated them.
To me, the way that it looks, the chart itself, just is different. It's a different way of thinking about a set of numbers. All right? But it says the stem, such as the leftmost digit, and the leaf, such as the rightmost digit, is going to be put in a chart like this. All right? Here's the set of data. I know if I click on it, it's going to probably go to the set of data. These are all those IQ scores that were in table 2.1. And they are a couple sections back. Look at this right here. This represents 50 and 56. At first look, it just looks like 5 and then 06. But this represents 50 and 56. It looks like there were none in the 60s. But then this number right here, this represents 70, 72, 73, 74, 75, 76, 76, 76, 76, 76, 77, 77, 78. Okay? So it's just a different way to organize data. I guess it would make the set of data a little shorter, you know, a little smaller. But it just doesn't, I don't know, I don't see how that could be used in the real world to show something to someone to convince them of whatever point you're trying to make. I mean, you can see right away with a a stem and leaf plot or stem plot here, that there's not a lot of 50s, there's no 60s, there's no 130s. You can see, you know, the majority are in the 80s and 90s. You can see things like that from it. But to me, it doesn't represent the data in some flashy way. It's kind of boring. Not like this class though. This class is awesome. So I promise you the math will get more intensive, and I will start getting into it a little bit more as the sections go on. All right, a bar graph. Everyone taking this course at some time or another you've seen a bar graph. I don't know. You might need to write the definition down if you don't know what a bar graph is in general. But a bar graph, it says, uses bars of equal width to show frequencies of categories, categorical or qualitative data. So, an example: median income by gender, by years. So you can see the males make more every year. The females make less. That's not a good thing. I'm not proud of that. I think I'm all for equality. I think that that everyone should make the same if they do the same job. So you can see as the years increase, though, the median income has increased for males and for females. Hey, I would be fine if my wife made. We're both teachers. I would be fine if my wife made more money than me. We are paid on the same scale. It's just that we teach at different places, and she teaches her extra classes somewhere else, and I teach my extra classes here. So, but yeah, I'm fine with equality for everyone. Not only fine, but I encourage it. All right. Pareto chart. When we want a bar graph to draw attention to the more important categories, we can use the Pareto chart, which is a bar graph for categorical data. So, you know, you can see here this chart. I mean, each bar has widths, but this chart is a Pareto chart and shows, and you see it emphasizes on these qualitative topics down here. And when you want to do something like that, you can make a bar graph called a Pareto chart. Nothing fancy. No. They could be in any order at all. They just did it this way to catch your eye so that you can see this is larger here. And then you'd see, okay, well that's what contributes to happiness the most. Pie charts. This is something else I'm sure that you've seen. I recently saw a pie chart breakdown of the time allotted to different topics of the average NFL football game. And it was very interesting to me because the biggest slices of the pie were, I knew what one of them was going to be without a doubt. It was going to be commercials. You know, that's going to be a big part of any game because they have sponsors. You know, those people pay money to have their commercials shown. So that's going to be one of the largest parts. Another large part, the one that I didn't even really think about, is the camera footage of people just standing around or cheering. They show football players on the sideline, cheerleaders on the sideline, fans in the stands, about the same amount that they show commercials. One of the smallest ones, though, was action on the field, 11 minutes a game. So in 11 minutes that you're watching the game is the actual action going on in the football game, on average, for an average NFL game. And that was, you know, it's a study that's been out there. You could just look on Google and type in, you know, breakdown of time used in NFL games, and I'm sure you can find the study. It's pretty neat. You wouldn't think it, but now that I think about it, I think about the study, and I watch a game, I'm like, yeah, we're just sitting here watching cheerleaders or watching people stand around and talk about plays, or watching Peyton Manning go up to the line and say, Omaha, Omaha. Mike is Mike. Mike is Mike. But, yeah, so it's kind of interesting. But a pie chart can be used to show stuff like that. I know at an early age, pie charts are used a lot because they're, you know, we kind of think about a whole pie, and your piece of the pie, is it a small piece or is it a big piece? So the larger the piece of the pie you have, then the better sometimes, you know. Well, in a pie chart like this, the larger the piece of the pie, it's that same data we were looking at, what contributes most to happiness? The family partner. That much, you know. Sports, that much. I think my piece of the sports pie would probably be about like that. Then the rest of it would probably be family and work. My work would be bigger because I enjoy my work a lot more than that much in my life. My friends would probably be a little bitty slice because you eventually lose contact with all of your friends, believe it or not. Not all of them, but most of them. Enjoy your friends while you have them. You'll be lonely like me one day. Just kidding. Oh, I've got more than enough to do, believe me. All right, a frequency polygon. Let's see. A frequency polygon uses line segments connected to points located directly above class midpoint values. So here's a very important point of, or important part of a frequency polygon, is that you have to know where the class midpoint value is. Remember the classes in a frequency distribution? You have to know where all the midpoints are. And then the points in the frequency polygon are right above those midpoints. You see, these are the midpoints for a set of data, the same IQ scores. These are the midpoints. The point is put right above the midpoint. And then you connect the line segments, and that makes a frequency polygon. Relative frequency polygon, just like a relative frequency distribution that we went over, you would have percentages. So you'd use proportions or percentages in that. Here's one here. So you have the percentage over to the side instead of the actual frequency. But it's still a frequency polygon. Alright, I always found this one interesting just because of the way it's pronounced. Here's your good Scrabble word. Does anybody play Scrabble with friends or something like that? I mean, I've got 3 or 4 games going on all the time just to keep my mind moving. And if maybe you're not a big Scrabble fan, but if you are, here's your word. Ogive. Alright, O-G-I-V-E. Just that extra letter may help you win one day. You never know. Alright, so it depicts cumulative frequencies. Remember we did a cumulative frequency distribution where instead of you giving the frequency of each class, the frequencies get larger and larger because it's a running total. Alright, so here's what the cumulative frequency distribution table would look like if you graphed it as an ogive. So you see the cumulative frequencies. So what does that mean? Nothing really spectacular, just that instead of a frequency you have a cumulative frequency. So as you go further to the right, the number is going to go up and up and up. So it's always going to increase as long as you have positive data values, because the frequency is getting larger and larger and larger because it's a total, a running total. Graphs that deceive. So you want to figure out a way to trick somebody with a set of data? No, of course we don't want to do that. But it says some graphs deceive because they contain errors. Some deceive because they are technically correct but misleading. That's the type of marketing tool that some of the big companies will use. They don't, maybe they want you to think they don't do it on purpose, but sometimes they'll use those to sucker you in. It says it's important to develop the ability to recognize deceptive graphs. Here we present 2 of the ways in which graphs are commonly used to deceive. A non-zero axis, that's what we saw earlier in the class, a few class meetings before this. That means the axis doesn't start at 0. See, it starts at 30 here. So it creates something that is really not there. You would think that the Honda Civic, gas-wise, was the best thing since sliced bread. You would think that the Honda Civic would go 8 times further than the Toyota Camry if you didn't pay attention to the numbers. This just says that the Honda Civic has 36 miles per gallon and the Toyota Camry gets 31 miles per gallon. I mean, if you drive a lot, it makes up a difference, but not that big of a difference, right? Between 36 and 31. Okay. But just by changing this axis, being non-zero, not starting with 0, it changes the way the data is perceived by the average person. We're not averaging here, though. Pictographs. You know, you can make something look larger than it actually is. You would think that this plane from 2010 was 3 times as big as 1984, and it might be. But you know, changing it just a little like that can make people lead to people maybe deducing the wrong thing. You could make one plane look like it was about to come apart, and then make the other plane like have gold trimming or something. I mean, that just in itself would make you think that they were better today than they were back then. There's all kinds of things that you can do, but that's 2 of those that could be used to deceive.